Hello and welcome everyone to the second session on WebAssembly. I hope you all attended the session about the history of WebAssembly on earlier. But if you haven't, don't worry, we won't need any of the information that you learned there. So this is a WebAssembly 201 where we want to dive a little more deeply into how WebAssembly works under the hood. And for that, of course, I'll focus on what we are doing here in the WebAssembly runtime team in Munich for Google, for Chrome, and for V8. So how does a WebAssembly file look like and what does it contain? A WebAssembly or wasm file contains platform-independent code as a binary format, which mimics a low-level stack machine. As it's platform independent, it doesn't know anything about the architecture that it's running on. So it doesn't know if it's running on an Intel architecture, an ARM architecture, PowerPC, or whatever. It doesn't even know if it's 32 or 64-bit. So because of that, it only has very basic data types like ints, floats, and SIMD vectors. So you can see we are indeed very low level. No matter whether you're running on 32 or 64-bit, you always have access to 32 or 64-bit integers and floats. So you don't really have to know how this is going to be turned into the target architecture. Pointers are indices into the array buffer. The array buffer is used as a substitute for the linear memory that you would use in your normal program. And instead of having a pointer there, we just count the bytes from the beginning and use these as pointers. So as currently the memory is limited to 4 gigabytes maximum, we can use an I32 to address pointers in our array buffer. So most of the optimizations can actually happen before we compile the code. So when we go from the source via our compiler tool Jane, creating wasm files and sometimes additional JavaScript files for the parts that cannot compile to wasm yet, we can do a lot of optimizations already. And most of the tool chains make massive use of that, which lowers the burden for us translating the wasm file into optimized code. However, there are certain parts that are architecture specific that we cannot really sort out. The most important one is register allocation, because we don't know what kind of registers and how many registers we have when we create the wasm code. However, of course, this is very important information that we need for creating then in the end the machine code. So for that, we do need to infer that information. And that's why we need to do the register allocation in our just-in-time compiler. So how does a wasm file look like? A wasm file mostly splits into two main parts. There are the header sections, and there are the code and data sections. The header sections define basically everything that the module needs to expose to the outside world, so the embedder, in this case, that's obviously JavaScript. And the data section contains the meaty bits. So this means these are the parts that likely make up most of your wasm file. So in the header sections, we have function types, imports, function declarations, tables, memories, global variables, exports, start function, and elements for table initialization. The memories, tables, and globals can be used to control the state of a wasm module from JavaScript. Imports and exports are used for calling across wasm and JS. So if I want to call a JavaScript function from wasm, I need to import it into my module first. If I want to call a wasm function from JavaScript, it needs to be exported from the module. The code and data sections then contain the function body implementations. And the data section contains data that we want to use for initializing the memory. For example, if we want to store some static data there. If I want to load a wasm file from JavaScript, I can choose in between asynchronous, asynchronous, and a streaming API, where obviously the streaming API is preferred because it matches more the function how data is normally loaded in JavaScript. So you can see here in this little example, I'm using a fetch promise that loads a wasm file. So this fetch promise I can then feed into WebAssembly.instantiate streaming, which triggers the streaming compilation. Additionally, I can give a set of parameters here that will define, for example, what I want to import and other things that I want to pass over. Once the promise that is returned by instantiate streaming is resolved, I will get in return the module, which is basically the compiled part of it, and the instance, which is the part or the environment in which the module will actually run. In this case, I only care about the instance, and in most of the cases, this will be the same for you. The instance in this example has an export, which is under exports, which is a function called hello. We'll see in a bit how we implement that, but you can imagine that you can then do all kinds of things, calling functions, passing parameters, setting data, reading, writing memory, etc. So this instantiate streaming function will validate the module, will decode it, compile it, and finally then instantiate it. So let's start with the typical hello world example, and in this case, hello to the wasm world. What you are seeing now is a text representation that we are using for WebAssembly. It's not the binary representation. So in order for this to run, we actually have to convert this to a binary format. However, the binary format is pretty hard to read for humans, so many people prefer reading the text format. You can see that we are using these bracketed S expressions here to define all our commands and definitions. So the module here is made up of imports in this case. So we have the memory import, which is a wasm memory, which is of size 1, where 1 is 1 page of 64 kilobytes. So this should be more than enough for us to work with. We also have to import another function called print from JavaScript, which will take 2 parameters, which are both integer. And then we define our own function, hello, which we will export to JavaScript. And this exported function will actually not do much. So it will just call the print function with the 2 parameters that are, in this case, hard-coded. So what this expression will do, it will put an i32 constant with the value 0 on the stack, then put an i32 constant with the value 18 on the stack, and then call the print function, which takes 2 parameters. So it will drop these two or pop these 2 parameters from the stack and pass them as function parameters. We also have a data section in the end, which contains the string that we want to pass. So in this case, it's hello wasm world, which is 18 characters long, as you can imagine, and starts at position 0. So once the memory is initialized and the module is instantiated, this will be preset in the memory as a static content. Of course, after that, we could be overwriting it, but that's not the goal of this example. So if I wanted to load this function, then what I would have to do is I have to instantiate the module similarly to what we have seen just before. For that, I have to go a little more out of the way than just calling this part below that we have seen, because we are expecting 2 imports, remember? We need the memory and the print function. And so we have to define these functions first. The memory is pretty straightforward. I can just call new webassembly.memory. You don't normally have to do that, but in this case, we want to access the memory from inside the print function. So it's best if we just pass it in the beginning and keep a reference to it. The print function itself takes the 2 parameters that we have defined, and it just takes a slice out of the array buffer that makes up the memory from position with length len. And these are the raw bytes, which we then can convert into a string using a text decoder. In this case, we are writing out to the document directly. But of course, you could add this to the DOM. You could write this to the console, whatever you would like to do. This shows a limitation that we have in WebAssembly, which is that WebAssembly, while it has all the possibilities to do computations, it doesn't really have an interface to the outside world. So very often we actually need to work with JavaScript function to mimic that. What happens then once it's loaded is that we are running a 2-tier compilation strategy. So our first tier is the streaming baseline compiler called Liftoff. It's designed for fast compilation time, about 10 times faster than the second stage, which leads to a quicker startup time. So the goal is really to get your program running as soon as possible. It doesn't do any optimizations and does very simple register allocation. We also use this for debugging, but obviously not for profiling, since it's much slower. It basically just takes the function body as it's delivered by the decoder and turns it straight into code without doing anything in the meantime. This works surprisingly well. Not only that, we get compilation times that are so fast that in most cases, the program is compiled as quickly as it's loaded from the web. But also the performance of that is actually pretty good. It's only about half as fast than the optimizing compiler, but that's already pretty close. The optimizing compiler, TurboFan, is the same one that we are also using with the JavaScript engine. It's designed for fast execution times and is about twice as fast as I mentioned earlier. It also produces about half the amount of code because it can optimize it further. It has a smart register allocation mechanism and has multiple steps that we go through. So after the function body decoder, we are constructing our sea of nodes graph, run optimizations on that graph, schedule the instructions, meaning bringing them into a linear order, selecting the instructions, and then also doing the register allocation in a smart way. And only then we are generating the code, which naturally leads to more optimized and more compact code. So the typical performance profile that you will see in a wasm application is that in the beginning, once we start, there will be a lot of parallel Liftoff compilations starting. And until those are finished, we can actually not start with the execution. Once they are finished, the instantiation will take place. So that's where we initialize the memory, etc. But in parallel, we can already start the Liftoff compilation. So this will be kicked off automatically in the background, and you don't have to care about that. Once the instantiation is done, we can start executing. And you can see in the beginning, those light green parts, we are executing mostly Liftoff code. But as soon as any of the functions finish compilation in TurboFan, we replace this function. And so from then on, more and more code will be executed in TurboFan. So this is a bit of an unstable phase where the performance will go up continuously. And only once all the TurboFan compilation is done, only then we will reach the stable phase where we run at peak performance. You can also see this in the performance profile here, where in the beginning we have a very short Liftoff compilation phase and then a longer TurboFan compilation phase. And right after the instantiation, the execution is already starting. Let's go into a more complicated example here, because I think this can help us a little bit trying to understand better how this can be used in reality. So this is an example where we not just call a function from JavaScript, but where we actually go through a very simple algorithm. So this is a very naive power function, which takes one parameter, which is the base, which is a double, so a float 64. And it takes an exponent, which is an integer, in this case, a 32-bit integer. And it returns then, of course, the result as a double as well. This function is, of course, nowhere meant to be efficient. It's a very naive implementation, but it's something that I think just has the right complexity to understand a little bit better what's happening within WebAssembly. We also define two local variables. And these local variables we call I, which is the index that we are counting in our loop, and the result, which we will return in the end. This just helps us writing a little more readable code. In principle, we could also try to put all of that on the stack, but that's not very readable and hard to understand. So I'm using here some variable names like $I, $res, $x, and $base, which only exist in the text format. Those variable names will not be present in the binary. So when we later look at the binary in Chrome, we will not see these names, unfortunately. So it will be basically numbered from variable 0, 1, 2, and 3. The actual function body consists of an initialization where we initialize I by setting it to the exponent. And we do that by getting the exponent from the local variable, putting it on the stack, and then setting the local variable I by popping the value from the stack. And similarly, we initialize the result with 1.0. The loop itself is actually rather simple. So the loop is just a block for us, which we know in the end will return the double value that is the result. All the logic, when do we break, etc., we have to explicitly write in the loop, similarly to how this would be done in assembler. So in the beginning, we just get the result, put it on the stack, and then we are also getting the index, putting that on the stack as well. We check if that index is 0. If yes, then we have this conditional branch, which will branch out to one level above the current level. So we are currently within the loop. One level above is then the end of the function. If the value is not 0, so if we still have work to do, we just continue with the next command. Remember that we still have here the temporary result on the stack. So we are going to put the base on the stack again and then multiply these two values. What will happen then is two values will be popped from the stack and the result will be pushed onto the stack again. And then we have to do some logic here about reducing the index, so subtracting one from the index to make sure that eventually the loop will end. The last command here, the br0, is then an unconditional jump or branch, which will just go to the beginning of the current block. So 0 is the current block, 1 was the block outside. So let's have a look at how that would look in the browser. And let's start with the simpler example that we had from earlier, the hello world example. When you execute that in the browser, you can see that it indeed writes hello wasm world to the document. But how is this done? If we open DevTools in Chrome, we can see that there is a wasm file loaded, and we can see the content of that wasm file. This looks pretty much like what we had put in from what you have seen on the slide earlier. It just contains a slightly different interpretation in text format than that was, in the sense that, for example, here this constant is really indeed pushed onto the stack first instead of using this bracket notation. Otherwise, it's pretty much the same thing. We can also set breakpoints here. And if I reload the page, I will, of course, eventually hit that breakpoint. And we can see here what we have available. So in the scope here below, we can see this is a wasm scope. So we have wasm information here. We have the memory that we have pre-initialized with our hello wasm world, as you can see here. So this is the ASCII code corresponding to these. And the rest of the memory is just initialized with zeros. You can also see that, of course, there is the hello function that is being exported. And we can see local variables. In this case, we don't have any local variables. We'll see in the next example where we have some. And we can see the stack. The stack currently doesn't have any content. But if I step to the next function, you can see that now the 0 was put onto the stack. If I go to the next function, you can see that the 18 was put on the stack. If I go then to the next function, you can see that the stack was dropped because the call instruction popped these two parameters. And you can continue like that and just step into the JavaScript code as well. So whether you're in wasm or in JavaScript, it's all very transparent and you can step through all these parts. So let's have a look at the more complex example from earlier. So this is the power example, and you can see here in my example I've used 1.414, which is a close but not great approximation to square root of 2, and I took the 16th power of that, and we get something that is close but not great to 256. So the code seems to work. Similarly to what I did before, we can set a breakpoint and step through that function. So let's reload that, and you can see we are now paused in the debugger, and we are in the first line. You can also see that unfortunately the variable names are not visible here anymore, so they all have very generic names. And I can step through that and see how the stack gets populated. So you can see the local variables change their values, and as we step through, for example, here we have the preliminary result 1, and the current remaining number of iterations 16 on the stack. And now we are comparing 16 to 0, which is false, so it's being replaced by a 0 value. And then we are putting the next value on top, so the branch pop value. We'll see if it needs to jump elsewhere. It doesn't, so we are putting the base on top. We have these two values. We multiply them in the next step and then get the result pushed on the stack. And we can do this again and again, going through all the iterations here. And in the next step, when we arrive here, after the multiplication, we have approximately 2 here. So this works very nicely, and this already allows you understanding better what's happening within wasm when you execute it. The generated code in Liftoff is pretty faithful to the wasm code that we have put in. So basically, for every instruction in wasm, more or less, it will output a number of instructions in assembly code. You can see here we have a lot of the yellow code, which is instrumentation code, and also quite a lot of application logic, which seems a little excessive. There are quite a few jumps here, more than maybe you would expect. That's because we also have, for example, to check if there are interrupts that we need to follow up with, and then call functions that are able to handle that, because we don't want, of course, a wasm application to hog all the CPU power and never react anymore. If we look at the TurboFan code, you can see that it's much more compact. So not only that there's fewer instrumentation code, there is also much more compact application logic that is being generated from here. So that shows you that the optimizations that are happening indeed do change the code quite dramatically, make it more compact and faster. What we also need to take care of is multi-threading. And while multi-threading is not yet part of the standard, we have already implemented it. How can you implement multi-threaded code in an engine that is embedded in JavaScript? The way we do that is that we use our main thread, but also use worker threads. So these are kind of similar to web workers. Each of these threads will have their own JavaScript heap and will have their own wasm stack. So that's the actual execution stack. But they will share certain things. So they will share the same memory. And we can achieve that by, instead of using an array buffer for our memory, we'll use a shared array buffer. That way, it can be accessed in both the main and any of the worker threads. We also have an internal structure, which is called the native module. The native module contains all the code, and especially the compiled code. So we only need to compile the code once, and we don't have to compile it for each of the threads. And it will only reserve memory once, since this is indeed shared in between these two threads. So this way, these two threads can work on the same memory, so the linear memory, and can reuse the same code, even though they are actually quite isolated from the JavaScript side. Naturally, using this mechanism adds a little more overhead to multi-threading than what we are used from POSIX threads, but it works pretty well. So you might ask, yeah, how about other features that one could think of? And I just highlighting 3 features here that I would like to talk about very briefly. One of them is SIMD. Similarly to what we did with the multi-threading, we already implemented it and shipped it, even though it's in an early phase. So you actually can try out SIMD if you're interested in that. At the current time, the proposal supports 128-bit SIMD instructions. We're also working on garbage collected languages. So this is much earlier in the prototyping phase. So we have a working prototype of that based on early proposal, but the proposal process is still in the making and things are still being figured out. However, it's a very exciting field to come for WebAssembly. And finally, what about debugging and profiling? You have already seen that we can do some low-level debugging, but actually more higher-level debugging features are in the making. So you can say set breakpoints based on the original source code, for example, C++, and inspect the variables that you have defined there instead of having to go on this low level. You can also profile your code with the original function name so you can see where the time is being spent in case that leads to unexpected behavior compared to what you expected from your native application. And these features are actually already quite ahead and quite useful. So that finishes a bit the round trip I wanted to give with a slightly deeper dive on WebAssembly. And now we can go to some questions that you hopefully have posted in the meantime. And I will try my best to answer them as good as possible. Okay, that means that either there is a lot of stuff to digest here, or it was all very clear. So I hope it's a mixture of the two. All right. Okay, then thanks a lot for your attention. And if you're interested, feel free to contact me or just check out webassembly.org or the V8 page for more information on WebAssembly. And yeah, I hope you have fun and have a nice day.